So in this video, I wanted to show an example of solving an exact differential equation using the integrating factor. You can go back and watch the first video if you want to know sort of why this works, or you can just start here and look at an example. Sort of depends on what you need. So I've got here an equation, a differential equation, and it is already in standard form, because I've got dy dx, and I've got y times a function of x, and I've got q of x here. So this is our exact form, dy dx plus y times one function of x equals another function of x. So you want to identify what those pieces are, and you're going to multiply by the integrating factor e to the integral of p of x dx. Which here, don't forget about that negative. It's a small detail. You want to go to the antiderivative of tangent of x. Okay. Some people memorize what the antiderivative of tangent is. That's one option. Or if you want, you can just recall that tan is sine over cosine. And so a u substitution for cosine of x is going to cancel out with sine of x, because the derivative of cosine is negative sine. And so then you get the integral of negative 1 over u du. And so you get negative natural log of the absolute value of u, absolute value of cosine x, like that. Okay. So then I'm going to use this answer that we just got as there, noticing that there's a negative sign and another negative sign, so we actually get a positive sign. So we're going to multiply everything by e to the natural log of cosine x, and that comes out to just be cosine x, absolute value cosine x. At this point, we need to sort of decide if we are going to deal with the positive or the negative arm of it. And so you can look at the initial condition. And the initial condition given in the problem is, I'll just pop it up here, we'll use it later, that y of 0 equals 1. And if you plug in x equals 0, you'll see that this is a positive value, because cosine of 0 is positive. So I'm just going to get rid of those absolute value bars and call it like that. So we're going to multiply everything by cosine of x in our original differential equation. And that's really nice. So now we have cosine x times dy dx minus y times sine of x. Remember, tan is sine divided by cosine. So if I multiply by cosine, it cancels out the denominator. Secant is 1 over cosine. So if I multiply by cosine, I get negative 1. The left side turns out to be the product rule of cosine of x times y, because you can see here we have f times g prime, and then f prime times g. The derivative of cosine is negative sine, and the derivative of y is dy dx. So now what we do is integrate both sides with respect to x. So cosine of x times y equals negative x plus c. So then you can apply your initial condition that y of 0 equals 1. Y of 0 equals 1 means x equals 0. So cosine of 0 times 1 equals negative 0 plus c. That means that 1 is equal to c. And then we can solve for y by returning to here, subbing in c, and dividing by cosine. So y equals negative x plus 1 over cosine of x. So if I wanted to use that for anything else, I could. Like if I wanted to predict what the y value is when x equals pi or 100, you can plug it into that formula there. So thanks for watching. Please comment if you have any questions.